here we are giving temperature. Okay, so we have given temperature equals to 190 degrees Celsius. I hope you have your property tables with you. And then we are giving pressure also equals to 2,500 kilopascal. Now, we are interested in determining the internal energy and then the state of the fluid. There are two options by which we can approach this question, actually. So one option is that we can, in order to determine the state of the fluid, we can use, let's say, find the saturation temperature, okay, using the, what do you call it? The TV diagram, like this. Okay, so finding T saturation at 2,500 kilopascal, or this gives me, 2.5 MPa. So we will have to look for T saturation. What is the T saturation here? How much is this? What was it? Ayman, can you help us?
223.95.
223.95. Okay, thank you. Degrees Celsius. So we discovered that the saturation temperature is greater than T saturation. Okay, is greater than the temperature T. So it means that our fluid is going to be in this state. Okay, so now this is our T saturation, and then our temperature T is given over here. So this is T saturation. So this clearly shows that the state of our fluid is compressed liquid state. Okay, so now we have to go to the compressed liquid state at pressure of, let's say, 2.5 megapascal and temperature of 190 degrees Celsius. We need to find the, yes, so let's conclude over here. Since T saturation is greater than T, this implies compressed liquid state. Okay, so now we have to go to the compressed liquid state, but again, if you have difficulties in doing this, okay, maybe, I think, Ayman, we will need interpolation over here, right? Is it? Hello?
Yes, but at compressed liquid table does not have 2.5 megapascal.
Okay. Oh, yes. So now, in this particular situation, yes, thank you very much. So I do not have my property table with me here. So because of the fact that we, in the compressed liquid state, we do not have 2.5 megapascal, then we are going to make an assumption that the fluid is no longer at the compressed liquid state. We assume it to be in the saturated liquid state. So at that particular point, we are going to look for UF. So now we're going to look, it means our U is going to be equal to UF at the given temperature, not the pressure. So that gives us 190 degrees Celsius. What is the UF over here? Can you tell me what is it? Anybody?
806.00.
806.00. So kilojoules per kilogram. Okay, so another way by which you can approach this question is like this. Somebody can decide to say, okay, I'm going to determine P saturation. Okay, I'll first of all find P saturation at 190 degrees Celsius. How much is this? Can somebody tell us? What is P saturation?
1255.2.
255 point what?
2.
0.2. So kilopascal. Now, looking at the PV diagram, we have a situation like this. So this is our constant temperature line. So the saturation pressure is this P saturation, but the pressure of our fluid, again, is in the 2,500. So 2,500 will be somewhere here. So again, it means the state of the fluid is in the compressed liquid state. You understand me? So the state of the fluid, again, is in the compressed liquid state with respect to this particular region, because P is greater than, so P is greater than P saturation at 190 degrees Celsius. So this implies that the state of the fluid is compressed liquid state. Okay, so then again, we have to go to the compressed liquid state at this particular temperature, at the temperature of T equals to 190 degrees Celsius and P equals to 2,500. Okay, so we are going to look for U. But again, if you go to the property table and the compressed liquid state, you're not going to find this. So again, the approximation will come again. But like I have told you, we are not going to use, don't do this. Don't do the approximation with respect to pressure. Otherwise, the difference is going to be too much, and then there will be error. So we are going to, instead, I'll advise you to rely on the TV diagram, okay, where the approximation is like this. So where we have the approximation like this. So where we have the approximation like this, instead of this. Okay, so here we are going to assume that the fluid, or you can also make an assumption that the fluid is in this state. So nobody will arrest you. Again, you find the UF over here, but at the given temperature, not pressure, at the given temperature, means at 190 degrees Celsius, you are going to find this UF. You understand me? So again, you have UF equals to, so at 190 degrees Celsius equals to, again, the value that we have above. You understand me? So whichever way you go about it, then you get 806.00. So this gives us 806.00. Okay? So you will discover that, please pay attention. If actually there exists the value of U in this region, and then if you compare it with UF over here at the given temperature, you will discover that the difference between this U and this UF is not going to be very, 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 very small. You understand? But here, we unfortunately, we cannot determine the value of U in the compressed liquid state. So we make the assumption that the fluid is in the saturated liquid state. You understand? So whichever way, if there exists, in actual fact, if there exists the value of U at this state, and then you find UF, the difference is not going to be so big. But if you find UF, let's say at a given pressure, let's say 2,500, okay, and then you determine the value of U over here, to be in this region. If you compare these two, maybe the difference is going to be about 100. You understand me? But if you compare this U and then this UF at the given temperature, the difference could be about 2 or even 1. You understand me? So don't make that mistake by finding the UF at the given pressure. The UF is always obtained at the given temperature. Okay, so I hope this answers the question. Okay, the one who asked me, who reminded me. Okay, so let us move on to a very important question. Okay, so before we start for the lecture for today, let's see over here, PowerPoint. Yes, so we have already started with chapter 3. Okay, and I would like to discuss this particular question in chapter 3. Yes, this particular question. Okay. So can you see the question clearly?
Yes, sir.
Okay. So now, in this particular question, we are told that, yes, again, I think for the sake of those who were not present last time, let me just introduce you to what we did last time. We look at the first law of thermodynamics and its application to closed systems. Okay, we did look at heat transfer, work transfer, okay, and then we have mass transfer. Okay, we also did consider the application of the first law, okay, in a cylinder, piston cylinder arrangement. Okay, so we considered different forms of work, electrical work transfer. We considered also shaft work and all these things. Okay, so this particular question, okay, will give us idea about what the application of the first law of thermodynamics, okay, in regards to closed systems. Okay, so in this question we are told, pay attention, a piston cylinder device, okay, initially contains 200 kilopascal, so of a gas. Okay, so let me sketch it carefully over here. We have a cylinder. Initial state of the cylinder is like this. Okay, and then we have piston. So piston is there is a spring over here. Okay, you have a spring over here which is suspended. Now, the pressure is given P1 equals to 200 kilopascal. And at this state, a linear spring that has a spring constant of 150 kilonewton. So K, the spring constant is 150 kilonewton per meter. It's touching the piston, but not exerting any force on it. So it's just like this, that we have a piston cylinder, and then here we have a gas. So the gas is exerting some pressure on the surface of the piston. So it is like this, that the piston is resting on top of this gas, and then the spring is just touching it. However, the spring is not exerting any force on the piston. So it's just touching it. It means it is loose. There is no tension inside the piston. You understand? So now heat is transferred to the gas, causing the piston to rise. So now you see that whenever you transfer heat, let's say Q into the piston, what happens to it? So temperature is going to increase. Pressure will be building up. Okay, so now, but what we are told is that it causes the piston to rise, and then to compress the spring until the volume inside the cylinder becomes double. So now we have state 1 over here. Since the parameters of the piston is changing, initial volume V1 equals to 0.05 meters cubed. So the moment you transfer heat to it, and if any of the properties of the fluid changes, then the system will move to a new location called state 2. And at this state 2, we'll have a situation like this. Okay, so we have a situation like this. So now there is tension in the spring. Okay, so we have the piston has been displaced through a certain distance. So initial displacement is this, and this is the final displacement. You can say the initial volume, this is V1, and then the final volume, V2, is given by this. Okay, so now we are told that if the cross-sectional area of the piston, so cross-sectional area, this one is 0.2, area equals to 0.25 meters square. Now, determine the final pressure inside the cylinder. So we want to find P2, that we don't know. The total work done by the gas. So we want to find the total work done by the gas. Okay, so now that is W total by the gas. So first thing we need to know over here is that we need to establish or find the properties of the fluid at state 2. Okay? One information is that, so let me draw the diagram, the PV diagram in relation to the history of this particular question. So I'll draw the PV diagram just to give you a clear idea of what is happening. We have PV diagram over here. Okay. So we have, let's say, PV diagram over here. So initial volume of the fluid, there is the initial volume. Let's say initial volume is V1 equals to 0.05 meters cubed. Okay. And then initial pressure, P1, is given by P1 over here. Now, as we transfer heat, so heat is transferred to the piston, Q. What happens is that it is going to push this piston upwards. Okay? So if there is no spring, attached to the piston would have been expanded, or let's say move upwards freely, and it would have been a constant pressure process. You understand me? It could have been a constant pressure process. So volume would have increased, pressure would have been constant. So we could have a situation like this, in which the final volume is going to be here. We'll have our V2 over here, which we don't know. Okay, but in this situation, it is not a constant pressure process. Why? Because when, let's say, the piston is trying to rise, then the spring is pushing it backwards. You understand? So this pressure is going to increase. Assuming, let's say, you have a very rigid vessel, whose initial pressure is P1. If you add heat to it, Q in, so what will happen to the pressure? Pressure is going to increase, isn't it? So because the gas inside the closed system has no any degree of freedom to expand, or to expand the outer surface of the cylinder. So the pressure is going to increase over here. You understand? So the same situation is what we find over here. If in the absence of this spring, if we add heat to it, then pressure could have been constant, because as let's say, if the pressure want to increase, then the piston will move up, and then it is going to offset the increase in pressure. So pressure remains constant at that particular state. But here, because of the presence of this piston, it is going to increase the pressure. So we will have a situation like this. We will have a situation. It means that for this particular situation, we will have both increase in pressure and increase in what? Increase in volume. Okay. So it means we're going to have increase in volume. Sorry. So volume is going to increase and pressure is going to increase as well. So we have a situation like this until finally we come to this final pressure. So this is going to be the diagram, the PV diagram for this particular question. If it were to be a constant pressure process, then the work done will be bounded only by this area. But since because of the presence of this spring, there will be increase in pressure and increase in volume as well. So the line will be moving in this direction. And now we need to find the final pressure. So the pressure over here. Okay, but we know the initial pressure is P1 equals to 150 kilopascal. Now, coming back again to the piston, let's see. To find the final pressure, first, let us find, we are going to look for the displacement of the piston. So the piston will be displaced through a certain distance. So let us draw. Initial piston is this. Okay. This is the initial one. And then the final one is this. Okay. So again, I have. Okay, so this is the initial volume, and then the final volume is this. Okay, so final volume, okay, V2. Okay, we are told equals to 2 times V1. That's the final volume. Okay, and this gives me 2 times 0.05. Okay, and this gives us what? If you multiply this, gives us 1 liter cube. Okay, so if you look through the question again, we are told that at this stage, okay, so now heat is transferred to the gas, causing the piston to rise, and then compress the spring until the volume inside the cylinder doubles. Okay, so it means the final volume of the cylinder equals to 2 times the initial volume. Okay, so now the displacement of piston, and both piston and spring, okay, is given by, so now you see initial volume, let's say this is V1, final volume, this is V2. Okay, so when the piston is moving upwards, it travels through a certain distance. So let's say this distance is given by X. Okay, so now it means this distance is the same as changing V2 minus V1. So delta V equals to V2 minus V1, which equals to what? X. Okay, so how do we determine this delta V? If I know this length, which is X, and if I know the surface area of this piston, which is A, so area times the height, that is going to give us the volume. You understand me? So the volume of the displacement. So the volume of this region, that's what we are interested in. So it means that our X, okay, or the change in volume, delta X, sorry, delta V equals to X times the area. Okay, so equals to X. Oh, sorry, I will not equate this to X, sorry. So this is a blunder over here. So this is, sorry. So, and delta V equals to V2 minus V1. Okay, so now how do we determine delta V? Delta V is nothing. It is the displacement, X times the surface area. That's the surface area of the piston. Okay, so now in order to find this X equals to delta V divided by area. So that gives me a change in volume, V2 minus V1. So we know that this is supposed to be 0.1. So 0.1. Again, this is supposed to be 0.1. Sorry, equals to 0.1. Okay, so this is V2. And V1 we know already. V1 is 0.05. So we have 0.1 minus 0.05 divided by 0. That's the area, 0.25. So this gives me 0.2 meters. You understand? So that's the distance covered by the piston in moving from V1 to V2. So now we need to find the pressure applied on the piston. So it means that we need to find a force. Okay, force applied, okay, or force applied by spring, okay, at state 2. At state 2. Okay, this is given by F equals to K, the spring constant, times the displacement. So here the spring constant is 150. So this gives me 150 kilonewton per meters times the X, which is 0.01. Okay, so let me see over here. We have X, 0.2. So that gives me 0.2. 0.2, okay, meters. So this finally gives us 30 kN, kilonewton. So now this is the pressure exerted by the spring at state 2. So now if you want to find the pressure, what is the definition for pressure? Pressure is force per unit area. Okay, so now this gives me 30 kilonewton divided by the area, which is 0.25 meters square. This equals to 120 kilopascal. Okay, so now this tells us, oh, so somebody want to enter the class. So 1 minute. Okay. So wait. Okay, so let's proceed. Okay, now we have got the pressure, the final pressure. Okay, now what we are going to do is that we're going to add this pressure. So P2, the final pressure, is going to be 200 kilopascal plus 120. This gives us 320 kilopascal. Let me explain this part to you. So you see, initially, the initial pressure over here is 200 kilopascal. Okay, but as the piston is forced to move up, okay, in other words, as the piston moves up, slowly, there will be some pressure building up within the piston. You understand me? So as a result of this, the pressure which is exerted on the piston to raise it up, that pressure corresponds to 120 kilopascal. So we're going to top up that pressure with this one to get 320 kilopascal in this way. Okay, so it means the final pressure over here is nothing. This P2 equals to 320 kilopascal. in this way. So that's the final pressure. Now, let's see. We have to determine, that's the final pressure, which the question asks us to determine. Now, let us find the total work done. The total work done, again, I'll draw the PV diagram. Total work done is given by the area under the curve. So initial situation is like this. Okay. So we have curve number 1 is this, curve number 2 is that. This is the PV diagram. So total work done, W total, equals to the area under the curve. So area under this curve means equals to the area A1 plus A2 equals to A1 plus area 2, like this. Okay? In other words, I will say, instead of using area, I'll say W1 and W2 equals to, so W1 plus W2. Okay, so now let us determine W1. W1 is nothing equals to the area under this curve, which is given by this is V1 and V2 times this distance. So we know P1 equals to 200 kilopascal. So this gives me V2 minus V1 minus V1 times pressure P1. So then that gives me V2 is given by 0.2. Okay, sorry, 0.1. So we'll have, and I'll bring the pressure first, 200 kilopascal. Okay, kilopascal times 0.1. 0.1 minus 0.5. 0.1 minus 0.5. Okay. And then this eventually, this gives me, let's see, over here. Oh, sorry, it should be 0.05. It should be 0.05. 0.05. Okay, 0.05 this way. So if you calculate this carefully, you're going to get, and let me see, 10 kilojoules. 10 kilojoules. And then we will determine the area under this curve. So the area, this is a triangle. Area of a triangle is half, okay, times the height, times the width. Okay, so in other words, I'll get half times the vertical distance. Okay, so this distance. So you know the pressure over here, P2 equals to 320 kilopascal. So this gives me vertical distance is given by P2 minus P1 times horizontal distance, V2 minus V1. So this gives me half 120. So this gives me 120 kilopascal times 0.1 minus 0.05. So eventually, so this is meter cube. So this gives me 3 kilojoules. So now the total work done in using pushing the piston upwards, W total equals to 10 plus 3, which equals to 13 kilojoules. Okay, so that is it for the first part of the question. If we go down, see, the final pressure we have already done, then the total work done by the gas. Now we want to determine the fraction of this work done against the spring to compress it. So that's very easy. So it is the same, that is the 3 kilo and the 3 kilojoules. Okay? The work done, okay, necessary to push the piston, okay, and up to its final state. And that is equivalent to the work done by the piston, okay, in moving from state 1 up to stage 2. So the final part is this. So the work done for the C part, okay, is given by 3 kilojoules. Okay, so that's it for this particular question. Okay, so I would like to ask if there is any question from any of you. Okay, otherwise then immediately I'll move on to the slide presentation. Okay, so if there is any question, please let me know immediately. Otherwise, then I'll move on to the presentation slides. Okay. Okay, so if there is no question, then I think I will continue with the slide presentation. Okay, let's see. So, stop presenting. Then I'll move to the slides. Okay, so here, I think last time we stopped somewhere. We stopped somewhere here, moving boundary. Yes, we discussed this already. Let me see. Yes, so I think, can you remember me? I think this is where we stopped,
Yes.
right?
Yes. Type of moving boundary work.
So let's continue. Yes, type of moving boundary work. Okay, so there are various types of moving boundary work. We have boundary work for constant volume process. Okay, boundary work for constant pressure process. And then boundary work for constant temperature process. Boundary work for adiabatic polytropic process. So the word boundary, when we say boundary work, it is the work associated with a moving surface. So the work associated with a moving surface means that the moving surface is, if you take this the piston, okay, the piston moves to and fro inside the cylinder. And this is what we refer to as moving boundary. And because of this movement, okay, different thermodynamic processes exist. And because of this, we will have different boundary work. Okay? So first, we will look at constant volume process or boundary work for a constant volume process. Now, one fundamental thing we need to know is that, you see, sorry. If, let's say, we consider a piston cylinder in which initial state of the piston is here, if it moves through a certain distance, d, okay, it moves from this, say, initial volume up to the final volume, okay, then the change in volume, delta V, the delta V will be equal to this distance covered times the surface area, and that gives us A times D. You understand me? So now the force exerted on this piston in moving through this distance D is given by F equals to P times area. So now if I want to find the work done by the piston is traveling from, let's say, state 1 up to state 2, the total work done equals to force times distance, which is the pressure times area times D, which is equal to P times D. This is what we call Pdv work. So this is the boundary work. You understand me? And this boundary work is only for a constant pressure process. So later I'll explain what we mean by constant pressure for a boundary work like this. Okay, later on. Okay, so the fundamental information we need to know is that when a piston is moving inside a cylinder, then the work associated with the piston is given by this Pdv. Okay, so it's a very important equation. Okay, so now this moving boundary work can be written in this form. WB is the boundary work, and integrating. So if we assume that the piston moves through a certain distance, V1, up to a final volume, V2, then we can integrate over the whole volume, okay, to find the total work done, and which is given by this. So Pdv is the boundary work, and the unit is in kilojoules. Okay, so now if you want to determine the boundary work for a constant volume process, then we start from the basic fundamental. The basic equation is that, so we have a constant volume. This is a constant volume system. So the volume does not increase. So volume remains the same. Okay, so it means that initial volume and final volume implies V1 is the same as V2. So by definition, the boundary work, fundamental equation for the boundary work is 1 to 2 of P dV. So we can express this in terms of P into bracket V2 minus V1. Okay, so in this situation, if V1 equals to V2, so it implies that the boundary work for a constant volume process equals to 0. You understand? So it means the WB over here will be consequently equals to 0 because the volume V1 and V2 are the same. You understand me? So that is it for a boundary work. Now, if we apply now a process that undergoes a constant volume process is called isochoric process, or sometimes isometric. So this is very important. Isochoric process, adiabatic process, isothermal process, isentropic process. So one after the other, we will look into them. Okay, so isochoric process is a constant volume process. So now, if we look into the, let's say, our ideal gas situation or ideal gas equation. From ideal gas equation, we know that PV equals to mRT. And for a constant volume process, so if an ideal gas is undergoing a change of state, say from P1, V1 equals to mRT1 up to a new state, say P2 equals to, P2 V2, so P2 V2 equals to mRT2. Okay, you can establish a relationship between these two equations. That gives you P2 V2 divided by P1 V1, whichever way, equals to mRT2 divided by mRT1. So mR will cancel, and then for a constant volume, this and this will cancel. Eventually, we will have P2 divided by P1 equals to T2 divided by T1. So this equation is valid for an ideal gas equation for a constant volume process. Okay. Now, if, let's say, we want to solve this question, so I'm thinking of completing everything before we start the tutorials, so later on. Okay, so let's go one by one. Now, here, for a constant pressure process, okay, what is the meaning of constant pressure process? That is isobaric. Isobaric is a constant pressure process. So how do we initiate a constant pressure process? We have a piston cylinder over here. Initial pressure is this, as the mass, and then the working fluid is water. If you transfer heat to it, say Q in. Now, if we assume that the piston is a frictionless piston, then it means that this piston can move up and down without any friction. You understand? So it means if we transfer some amount of heat to this cylinder, it is going to cause this piston to move up. And when in doing so, it is going to maintain this constant pressure. It means final pressure is going to be equal to the initial pressure. You understand? This is how we initiate, let's say, an isobaric or a constant pressure process. If this piston were to be fixed, if it is not moving, if it is stationary, and you transfer more heat to it, the pressure is going to increase, and it is no longer a constant pressure process. Then the whole definition will collapse. So what is the definition or the basic, condition for a constant pressure process? It means that as you transfer more heat to the system, pressure has to remain constant. So initial and final pressure will be the same. So again, we come back to the fundamental equation. You see this W, that's the boundary work for a constant pressure, is Pdv. Pdv work is given by this. So this is a Pdv work. So which is equals to, if we integrate and then we bring the constant pressure outside, the integral sign, then we'll have dV. So we integrate dV, then that gives us P V2 minus V1. You understand me? So now, if a system is undergoing, so you see over here for a constant pressure process, the volume remains constant, pressure remains constant, only volume is increasing. In the previous question, the one we solved now, you see, we had a situation like this. So this situation means there is increase in pressure and at the same time increase in volume. That is, this situation occurs only when you have a spring attached to the piston. But here there is no spring, there is no resisting force that is opposing the movement of the piston. The piston is frictionless. it can move freely, so that at this particular state, then we can assume and that it's a constant pressure process, okay, like this. Yes, so, sorry. So now, if we come back to ideal gas equation, for any ideal process, okay, PV raised to the power n equals to a constant, and then n if n equals to 0. Okay, so if n equals to 0, then this is 1. So it means P will be a constant. So if you substitute the value for n equals to 0 into this equation, P will be equals to C. So similarly, if you consider an ideal gas, which is undergoing a change of state from state 1 up to state 2, okay, so for any particular state, we have P1 V1 equals to MRT1. And similarly over here, P2 V2 equals to MRT2. So again, you can develop a relationship between the two states. And then eventually we will have, for a constant pressure process, the pressures will cancel and the resulting equation is this. Okay? Yes, so again, we'll look at these questions later on. Now let us come to isothermal. What mean of isothermal? Isothermal is a constant temperature process. Okay, so in isothermal, let's say we consider, let's say, a piston cylinder arrangement, okay, in which the initial temperature of the fluid is this, and then the initial pressure is this, initial volume is also given by that, okay? So if the piston undergoes an expansion, a compression, yes. So initial state of the piston is this. So it is being compressed. So you see, compression means pressure is what? Pressure is increasing. You understand? So we are moving from initial pressure of this up to a final pressure P2. And then volume is also what? Decreasing. Okay? So one thing we need to know is that how do we ensure a constant temperature process? So we are compressing the gas. And from our knowledge of thermodynamics, whenever a gas is undergoing compression, the temperature will try to increase. Okay? So, but how do we ensure that the temperature remains constant? We have to take out some amount of heat from the system. So you compress the gas. When you compress the gas, the molecules of the gas will move with a high kinetic energy, and which will increase the thermal energy. The temperature of the system is going to increase. Okay, but since we want to conduct this experiment at constant temperature, immediately we will take out some Q out from it. You understand me? So this is the way we can ensure a constant temperature process. And for all constant temperature processes, this is the what do you call it? The way the temperature profile looks like. Sorry, the pressure profile. This is the way it looks like. Okay? So if we want to find what is the boundary work associated with the compression of this ideal gas, which is air. So now we come to the fundamental equation. Boundary work equals to integrating from state 1 up to final state, Pdv. Okay, so then eventually, let me see, if we replace this P by ideal gas. We know from ideal gas law, PV equals to MRT. Okay, so PV equals to MRT. And yes, from this equation, sorry for diverting a little bit, if you have PV equals to MRT, for a constant, for isometric process, sorry, isothermal process, it means temperature is constant. So temperature is constant. Temperature is equal to constant. So if temperature is constant, and then this R is ideal gas constant, and then the mass of the gas is also constant, it means the whole of these parameters are constant. So this will give us C. So for isothermal process, PV is always equals to C. Okay, so now from our definition of boundary work, we have integral 1 to 2 of Pdv equals to integral. I'm going to replace now wherever I'll see P, so P will be equal to C divided by V. So wherever I see P, I'll replace it by C divided by V. Okay, so now I'll have C divided by V of dV, integrating from 1 up to state 2. So if we integrate 1, C is a constant, so we'll kick it out of the integration sign. So now eventually we'll have C integral 1 to 2, 1 over V times what? dV. So eventually we will have integral of 1 over V is log of V. So you see, we have log of V. So the boundary work, WB equals to C log of V2 divided by V1. Okay, so now we can make a substitution for C. What is C? C, we know that PV equals to C. So now we can replace this, that boundary work equals to PV. It can be, you can replace it by P1V1 or P2V2. You understand? So this can be P1V1, then log of V2 divided by V1. Okay, so whenever you want to determine the, let's say, the work done for isothermal process, if you go and use, let's say, if you use this equation, if you use W boundary work equals to Pdv only, so then it is 0. You understand? So this is valid only for isobaric process. So, but for isothermal process, the valid equation to determine the the boundary work is given by this equation. P1V1 or P2V2 log of V2 divided by V1. Okay. So now, from ideal gas law, okay, we have PV equals to MRT. Now, if MR and T are constant, so it means P1V1 equals to P2V2. So eventually we can have this situation. And the boundary work can be expressed in terms of also P1V1. And because we know that V2 over V1 equals to P1 divided by P2. Okay, so we can make a simple substitution in this way. Okay, so let's move ahead. Now, we want to determine the boundary work for adiabatic. And one more thing, please, you have to be very careful. All the time, you should try to recognize the graphs that is coming along with these constant pressure processes. So for a constant volume process, So this is the graph. This is the situation. The graph is like this. Because the volume is the same. V1 and V2 are the same. Whereas for a constant pressure process, the nature of the graph is like this. And again, for a constant temperature process, okay, so for a constant temperature process, the nature of the graph is like this. Okay, so the pressure increases in this way. And then we have for a constant of adiabatic. So what is adiabatic? Adiabatic is a situation where there is no heat transfer into or out of a thermodynamic system. So you can imagine a highly insulated thermodynamic system. So that is thermoflux, for example. Okay, these are adiabatic systems or an adiabatic process. So now let us develop the equation, okay, the boundary work for an adiabatic process. Now we know that the basic definition for boundary work is given by this integral from from V1 up to V2 of Pdv. So now for all adiabatic processes, yes, all adiabatic processes again are isentropic process. You understand? All adiabatic processes are isentropic processes because we have noted that the let's say the change in entropy, maybe let me divert a little bit, the change in entropy of an ideal gas is always equals to the integral of dq over the absolute temperature of the system. So this is the amount of heat added to the system, and this is the absolute temperature. The change in entropy, this delta S is the change in entropy. And for adiabatic process, for adiabatic process, so adiabatic means there is no heat transfer. Immediately you tell like this, Q equals to 0. You understand? So if Q equals to 0, then it means then the whole of this is going to be 0. So eventually, so therefore we will have delta S will be equal to what? 0. And if delta S equals to 0, it means, so what is the definition for delta S? It is S2 minus S1, so which is equals to 0. You understand? So it means the change in entropy between the two states is the same. Means S1 equals to S2. And any process where the change in entropy is the same, where the change in entropy equals to 0, or let's say S2 equals to S1, then such a process is referred to as isentropic process. You understand me? So in chapter 1, we did look in detail. I explained what we meant by entropy. Entropy is the degree of irreversibility of a system, okay, or the degree of disorderliness of a system. But in this case, we'll go more into the degree of irreversibility of a system. It means when a system is more and more irreversible, then the change in entropy increases. But under reversible condition, then the change in entropy equals to 0. So we have clearly stated over here the classical definition for change in entropy of an ideal gas is given by the integral of dq over the temperature, where Q is the amount of heat transferred to the system and T is the absolute temperature. So now if the process is undergoing an adiabatic process, so it means then Q equals to 0. If Q equals to 0, then delta S equals to 0. If delta S equals to 0, then it means that the process is isentropic process. So all adiabatic processes, again, are isentropic process. And they are governed by this equation. PV equals to PV raised to the power K equals to C. Okay, so PV raised to the power K equals to C. And So if we so let me delete this part so then we can have more space. Yes, so now if we want to develop the equation for this adiabatic process, which is the same as isentropic process, so we have basic definition for the boundary work is this. Now we make a substitution. We know that PV raised to the power K is equal to C. So P equals to C divided by V raised to the power K. Okay, V raised to the power K. So wherever we see P, we replace by this. So that is it over here. So integral of C divided by V raised to the power K. Okay, so now if we rearrange this equation, maybe for those of you who are weak, let us see we have the C comes out, then we have integral 1 over what? V raised to the power K. So now integral of V raised to the power K, this is the same as C integral of V raised to the power minus K. You agree with me? Okay, so now if I want to integrate this is going to give me, I'll add plus 1 to this, and then I'll divide by the denominator again. Okay, so now I'll have this equals to C into bracket. Okay, so V raised to the power minus K plus 1 divided by minus K plus 1. Minus K plus 1. So that gives me 1 minus, sorry. So I'll have minus K plus 1. Let's maintain it like this. Okay. So that, again, we have C, this equals to C into bracket, V minus K plus 1 divided by minus K plus 1 over here. All right, so now, if I push this C into the equation, what is C? C is PV raised to the power K. Okay, C equals to PV raised to the power K. Okay, so now let's see over here. Yes, so don't forget our limit of integration. So this is V1 up to V2. Okay, so if I put, assuming if I put V2 into this equation, if I put, it is going to be V2 minus K plus 1. Okay, V2 raised to the power minus K plus 1 divided by minus K plus 1. So eventually, I'll have, then again, I'm going to multiply by this P2 V2 raised to the power K in this way. Okay, so here I'm going to have a situation like this. Unfortunately, I don't have enough space to derive this particular, but let's see what we can do over here. So I'm going to replace this by P2 V2 equals to C. So I'll have, let's see over here, I'm putting the V2 inside, so I'll have V2 minus K plus 1 times this, P2 V2 raised to the power K. Okay? let me see. Let me open a different page so it becomes clear to you. Keep source. Let me open a different page. Yes, so this is much better. Okay, so we have the situation like this. Oh, sorry. Yes, so like this. Our final boundary work was like this. So we have W boundary work equals to C into bracket V minus K plus 1 divided by minus K plus 1. Okay, running from V1 up to V2. Now, what I'm saying is that if I push this, I want to push, multiply, or I want to put the limit of integration inside. If I put V2 inside, then I'm going to replace P2, V2 raised to the power K equals to C into, I'll replace it by this C. You understand? Okay, so then I'll have, let me see, or alternatively, we can take it this way. Okay, so now we have also P1, V1 raised to the power K, again equals to C. Now, I'll put the limit of integration into it. So I'll have a situation like this. W boundary work equals to C into bracket. I'll have V2 minus K plus 1 divided by minus K plus 1 minus, again, I'll have V1, okay, so that gives me minus K plus 1 divided by minus K plus 1, all right? So now what I'll do, I'll multiply this by, I'll multiply the whole of this by C, these two equations, this and that. But if I want to multiply this by C, I'm going to use this instead. So I'll have a situation like this. So boundary work will be equal to, will give me P2 V2 raised to the power K times V2 minus K plus 1, okay, all divided by minus K plus 1. Minus, again, if I multiply this C by V1, I'm going to use this. So I'll have P1 V1 raised to the power K, okay, times V1 minus K1 minus K1, no, sorry, minus K plus 1, all divided by minus K plus 1. Okay, so now what do you see? We have minus K here. Oh, sorry, we have K here and minus K, but this is multiplication. So it means they will cancel out. Then it will be left with what? V, if I have V2 times, this is K, multiplied by V2 K minus K plus 1. This is going to cancel out this one. And then the final answer will be V2 because of this one. Okay, so eventually we'll have WB equals to V2 over here. The whole of this numerator part is V2 divided by, we have minus K plus 1 minus, again, we have, again, if I multiply this by this gives me, oh, sorry, my P2 should be there, P2. So I have P1 and then V1 divided by minus K plus 1. Okay, so whichever way you want to rearrange this equation, this can be equal to, let me see, now it has a common denominator. So I have P2, V2 minus P1, V1 divided by 1 minus K. Or alternatively, you can say this equals to P1, V1 minus P2, V2 divided by K minus 1. You understand? So this is the derivation for this particular equation. Okay, so this is a very rich information that I'm giving you now. So please take note of it. Anytime you want to find a boundary work for an adiabatic or isentropic process, so it is given by the boundary work equals to P1, V1 minus P2, V2 divided by K minus 1. Okay, so this is very important. Whereas for the isothermal case, it is P1, V1 log of V2 divided by V1. Okay. Yes, so let me see. We will be stopping very soon. So this will be the last part. And then next week, we will look at some solutions. Okay, and then we will solve some, we will start with energy balance for closed systems. Okay, so let me complete this part for the boundary work. Now, the boundary work for a polytropic process. So what's a polytropic process? A polytropic process is a process that obeys the law PV raised to the power n equals to C. So this is different from PV raised to the power k equals to C. You understand? So this is an adiabatic or isentropic process. You understand? So where this K is a different value. You understand me? So, and now, for this particular situation, we have PV raised to the power n equals to C, where n is the polytropic index. Okay? And now, if you want to derive the equation for the boundary work for a polytropic process, it is similar to that of adiabatic. Okay, so here again, this is the law. Okay, PV raised to the power n equals to C. So P equals to C V raised to the power minus n. So again, the fundamental equation for boundary work is this. We make a substitution for P. Then again, we find the, what do you call it? The integral. Okay, just like I taught you before. You see here we have C V2 n minus n plus 1 minus, so it's the same as this derivation. It's the same situation, the same concept. There is nothing different related to this. The only thing is that here we have K, but in that equation we have K has been replaced by N. You understand? So over here, eventually, you see both equations are synonymous or similar in nature. Okay, so the boundary work for polytropic and adiabatic are similar in nature. The only difference is that for a polytropic, we have this is N, and then for adiabatic or isentropic process, it is replaced by K in this way. Now, another way in which we can express this equation is in this form. Okay, so we know PV equals to MRT. So PV equals to MRT. So if I have P2, V2 equals to MRT2, then P1, V1 equals to MRT1, I can just substitute in this equation, and then eventually I'll factorize MR out, then I have T2 minus T1, then divided by 1 over N minus 1. Okay, so for a polytropic situation, the equation could be this. Again, this is the nature of the graph for a polytropic process. So you see this is undergoing an expansion process in this way. Okay, so let's see over here. This is the summary of the boundary work that we have considered so far. Okay, so whenever you have a constant volume process, for a constant volume process, which is isochoric process, it is governed by this ideal gas equation. And similarly, isobaric process, the ideal gas equation is this. Isothermal process is this. All isentropic and polytropic processes are governed by P1 divided by P2 equals to V2 divided by V1 equals to T1 divided by T2 N divided by N minus 1. And with regards to the work, the boundary work, okay, isochoric process is this. This is isobaric, isothermal, both polytropic and isentropic are also represented in this. So for isentropic process, the value of N is equal to K. You see, I've explained to you that for adiabatic or polytropic process, adiabatic or isentropic process, they are governed by PV raised to the power K equals to a constant. You understand me? And then for a polytropic process, yes, polytropic process is also governed by this equation. Okay, however, they have same boundary work. The only thing is that depending on the situation, the N changes to K. Okay. So, and the nature of the graphs for PV diagram, entropy diagram, okay, is what we have on the slide. Okay, for situations where we have for a constant pressure process, we have this situation, constant pressure, and constant volume is given by the red line. And again, for adiabatic or polytropic process is given by this line, okay, which is the same as isentropic. And for isothermal process is also governed by this graph. Okay, so the same thing applies to the entropy section. Okay, so I think we will pause over here, and then hopefully, inshallah, next week we are going to continue our discussion. First, we will start with some tutorials, and then continue with the energy balance for a closed system. Okay, so if there is any question, please let us discuss. Okay, otherwise then I think we will stop over here. Okay, so let's have, let me see over here. Is there any question so far? Any question? Okay, so